Welcome back to the deep dive. Today, we are strapping in and going deep on the technology that runs the modern internet, the recommendation engine. Specifically, sequential recommendation systems. The tech that decides what Netflix shows you next or what Amazon thinks you should buy. Our mission is to unpack a really radical new strategy for making these engines smarter. It's called Alphafuse.
And the core challenge is trying to solve is this fundamental conflict between two types of data. First, you have what we call ID embeddings.
Okay.
Think of these as being learned from scratch, just from user interactions, clicks, purchases, views. They capture purely collaborative signals. People who bought X also tend to buy Y.
Right, the classic behavioral stuff.
Exactly. And on the other side, you have language embeddings. These come from large language models, LLMs, and they're derived from an item's actual text. Its description, its metadata, its reviews.
So this is the part that knows what an item is.
Precisely. An ID embedding might know that people who watch The Godfather often watch Goodfellas. A language embedding knows why. It knows they're both highly rated, feature-length crime dramas about Italian-American life.
Okay, so let's unpack this. Because historically, trying to fuse that rich, descriptive world knowledge with the sharp behavioral data, it causes huge problems, right? You usually end up breaking one to make room for the other.
You do. And Alphafuse really starts by identifying three fundamental headaches with the current ways people try to do this.
What's the first one?
The first is what the paper calls the degradation of semantic space. Think about the data coming from an LLM. It's incredibly rich, incredibly high-dimensional.
We're talking thousands of dimensions.
Easily. OpenAI's models can use something like 1,536 dimensions to describe one item. It's this super high-fidelity semantic sculpture.
And the behavioral space, the ID embeddings, that's way smaller.
Tiny by comparison, maybe 64 or 128 dimensions. And there's the problem. You're trying to force that giant, detailed 1,500-piece sculpture into a tiny 100-piece box.
Something's got to give. You're just crushing the details, aren't you? You're losing all the nuance that makes the LLM so powerful in the first place.
That's exactly it. You get a blurry, degenerated version of the original meaning. And that leads to the second headache, which is the underutilization of language embeddings.
Meaning they don't even use all that rich data?
Well, many methods only use the language embeddings as a sort of guide during the training phase, maybe to give the ID embeddings a good starting point. But crucially, when it's time to make a live prediction for a user at inference, that rich language data is often just thrown away.
Wait, that makes no sense. Why would you get rid of your best source of world knowledge right when you need it most?
Because actually integrating it is just too complex and computationally expensive. To avoid the degradation problem we just talked about, engineers often just simplify and fall back on the behavioral data that was only sort of inspired by the LLM.
So you've bought this incredible tool, this LLM, and you're essentially just using the instruction manual and then tossing the tool.
It's a great analogy. And that brings us to the third problem, which is a real engineering nightmare: involvement of auxiliary trainable parameters.
Okay, that sounds complicated.
It is. To try and bridge that gap between the huge semantic space and the tiny behavior space, models use extra bits of machinery. They're often called adapters or reconstructors.
Just more neural networks, basically.
Right. And these little adapters, they come with a huge number of their own parameters that need to be trained. Sometimes the adapter is even more complex than the recommendation model itself. It just bogs everything down. It's inefficient, it's slow.
So you're stuck. You either crush the semantics, you barely use them, or you build this clunky, inefficient machine just to hold them together.
That's the trilemma.
Okay, and this is where Alphafuse comes in with frankly, a brilliantly simple idea. Instead of forcing the LLM's data into a small box, they realize that the big box is actually mostly empty.
That is the absolute core innovation. Alphafuse's strategy is to learn the ID embeddings, the behavioral signals, inside the null space of the language embeddings. The null space. Explain that. The null space is the part of that massive, high-dimensional vector that contains little to no semantic information. By learning the ID embedding there, you can inject behavioral data without any risk of overriding or interfering with the precious semantic knowledge from the LLM.
Okay, that's clever. But how do you even find this empty space within a 1,500 dimension vector?
You use a very powerful mathematical tool called singular value decomposition, or SVD. You can think of it like a diagnostic tool, an X-ray for the data. It scans all the dimensions and sorts them by their semantic weight, how much meaning they actually carry.
And it splits the space in two.
Essentially, yes, it gives you two distinct subspaces. First is the semantic-rich subspace. This is where the big, important singular values are. It's where the LLM's core knowledge actually lives.
The meaning of the item.
Correct. And then you have the null space. This is the area associated with singular values that are 0 or very close to 0. It's geometrically separate. The language embedding has no projection onto this space. It's semantically sparse.
So it's the perfect empty canvas to paint on with new information, like user behavior.
Exactly. And I think this is the real aha moment. The research shows that for recommendation tasks, this null space is enormous.
Really? I would assumed a big LLM vector would be dense with information.
It's a common misconception. The dimensionality is high, but the actual rank, the amount of useful, non-redundant information, is quite low for this specific task. On the movie's dataset they tested, the null space was nearly 80% of the total space.
80%. So over 1,200 dimensions were just empty real estate.
Empty and waiting to be used. Alphafuse saw that what looked like a problem high dimensionality was actually the solution.
Incredible. So we found the empty room. Now, how does Alphafuse prepare these two separate pieces of information, the semantic part and the behavioral part, for the final fusion?
It's a two-step process. First, for the behavioral part, they perform what's called clipping the null space.
Okay.
Even though the null space is huge, you don't necessarily need all 1,200 dimensions to encode the behavioral signals. That would be inefficient for a standard recommender model. So they clip it, they shrink that space down to a more manageable size, like 64 or 128 dimensions.
Got it. So you've created a small, efficient behavioral zone inside that huge empty space.
Yep.
What about the other part, the semantic knowledge?
That part needs a bit of a cleanup. The second step is standardization of the semantic-rich subspaces. This is to combat a problem called anisotropy.
Anisotropy.
Yeah, you can think of it like an uneven distribution of information. It causes different items semantically to kind of clump together in the vector space, making them harder to tell apart.
So standardization spreads them out. It makes the distinctions between items clearer.
Exactly. It's like adjusting the contrast on a photo, makes everything sharper. The research shows that after standardization, the system could distinguish between, say, a crime drama and a fantasy film much more clearly, just based on the text.
Okay, so now we have our two components. Perfectly preserved, clarified semantic data, and a clean, isolated space for behavioral data. How does the final fusion work?
This is where the elegance really comes through. The standardized language embeddings, the semantic part, are completely frozen during training. They don't change at all. They're locked in.
Protecting the LLM's knowledge.
Right. And at the same time, the ID embeddings, the behavioral signals, are initialized and trained only inside their own clipped null space. They never touch the semantic part.
They're in their own sandbox.
Perfect way to put it.
Ah.
Then the final item embedding is just a simple concatenation of the two. You stick the frozen semantic vector and the trained behavioral vector together. And because they were kept separate, you don't need any of those complex, inefficient adapters we talked about earlier.
It's integration by total isolation. So the big question, what does this actually mean for the user? Does this clever math trick lead to better recommendations?
It leads to very significant gains. They tested it across multiple data sets, movies, toys, sports, and it consistently outperformed all the other state-of-the-art methods.
Where did it shine the most?
Well, one of the biggest wins was with the cold start user problem, a new user with no history.
Where traditional recommenders have nothing to go on.
Exactly. But Alphafuse excels here because it can rely on that pristine, high-fidelity semantic knowledge. If the system truly understands what an item is, it doesn't need a ton of clicks to make an intelligent guess.
That makes sense.
And the numbers back it up. For cold start users on the movie's dataset, they saw accuracy improvements of over 24%. That's a massive lift. It means a better experience from the very first click.
What about the other classic problem, the long tail problem? You know, those niche items that nobody ever clicks on.
Another huge area of improvement. Long tail items have sparse behavioral data, that's their definition, but they often have very rich textual descriptions. Their semantics are strong.
And because Alphafuse protects those semantics?
It can give those items a much richer, more accurate representation. And the results were, frankly, staggering. On some data sets, like fashion, they saw over a 200% improvement in key metrics for long-tail items.
200%.
It's rescuing items from obscurity. It's
Yep.
not just making popular things more popular. It's fundamentally making the catalog more discoverable.
And finally, what about efficiency? That third headache. Does this elegant solution actually run efficiently in the real world?
It does.
It dramatically reduces the number of trainable parameters you need.
Yeah.
And most importantly, its inference cost, the actual computation needed to serve a